without needing to go through the mechanisms, let's predict some tautomers. I'll give you guys one, for example. If I want to predict the tautomers that this compound can form, I need to consider where there are alpha hydrogens. If there's more than one place, remember aldehydes and esters only have one place that they could even possibly form tautomers. This ketone, though, it's got two different tautomers that can form. On this less substituted side, I can form a di-substituted enol. And on this more substituted side, I can form a tri-substituted enol. Which of these enols is more stable? Green. Any rationale? Yeah. Alkene is more substituted, so the enol is more stable. Okay. Why don't you work on the rest of those structures and determine any and all tautomers that can form. Someone want to redefine tautomer for us? Yeah, you read that straight off of the... Good work, good work. Chemically interchangeable structural isomers. I didn't have you guys start this, right?
No.
Okay. Hello. Do you need a sheet?
Oh, yeah.
Oh, sorry. You're welcome. Were you not here Tuesday?
No,
Were you able to catch up?
Yeah.
Good. Who put that chair there? Do you need a sheet too? Oh, my goodness.
I was going to ask for any extra. I can't find mine.
Absolutely. I've got plenty. Been waiting to put them to use. You're welcome. Yeah, we're working on this side. No, sorry, on the other side. And Tuesday, we just went through and we looked at where are the alpha hydrogens. And then, oh, I don't think I ever actually had you guys rank the acidities, did I? Whoops. We can go back to that one. But here, we're just looking at the tautomerization. Which, do you understand what it is? So these are structural isomers. So are these. And the structural isomerism comes from the alpha carbon. So what we talked about on Tuesday was the carbonyl carbon doesn't have a name. We just call it the carbonyl carbon. But adjacent to the carbonyl carbon, we have the alpha carbon. And the alpha hydrogens are surprisingly acidic. If they get deprotonated, the alpha carbon becomes in resonance with the carbonyl. And thus, it is more acidic. If it becomes in resonance with the carbonyl, then the carbonyl can actually act as a base and become protonated as an enol. So enols and carbonyls are tautomers of each other. And so we're just looking at that tautomerization process. We'll come back, we'll actually review the acidity. Whoops. So for now, see if you can identify an alpha hydrogen, a hydrogen on an alpha position, and then just draw the enol that results. Notice how in red, my alpha hydrogen is actually now on the oxygen. I went from a CH2 to a CH. So one of the hydrogens got transplanted. The green alpha hydrogen was the only one there. It got relocated. Do you think these are different?
Oh. No.
But it does say that there's more possibility, but they are the same, right?
Right.
Oh, so we don't have to draw them both?
Well, they're not really different, yeah. Same because
Same because.
identical. Same because same.
Same because.
Do you need a sheet?
No, I have it on my iPad.
Okay,
Thank you.
yeah. Uh-oh. I think you invented a carbon.
Oh. Yeah.
That's okay, I did that on my vintage.
Good work. All right, should we go through some of them? Can we name them too? I love nomenclature. I know. How about this first aldehyde? You can't name it? There's more than one way, because there's all sorts of fun little systematic common names you can give. Good. 2,2-dimethyl propanal. You can also call it, I wouldn't call it tert-butyl aldehyde. I don't like that name, because it just sums up that tert-butyl group, but it really never specifies a root. I think you could also call it tert-butyl methanal or tert-butyl formaldehyde, but those are like terrible names, right? Because it is just not identifying the longest carbon chain. 2,2-dimethyl propanal. How many tautomers could you find? How many enols from 2,2-dimethyl propanal? 0 tautomers. Why? No alpha hydrogens, and alpha hydrogens are the cause of tautomerization. Great. Can you name this compound? Three-phenyl propanal. Good. 3-phenylpropanal, how many tautomers? 1 tautomer. Now, it really depends on how you consider the stereochemistry to impact your tautomerization. Technically, we create an EZ alkene, so we could, in theory, create stereoisomers of the tautomers. But because these form in a non-stereo selective manner, they're going to form the most stable tautomer most of the time. All right, somebody new. Can I get a name for this compound on the bottom? Hept, like a heptagon. I don't know why, for some reason, I didn't think it was 7. Good, yeah. We don't have to describe where the aldehyde is because it's going to be at the end of the chain. But we do have to describe where the ketone is because it could be along a number of different positions. And then we still need that suffix before the suffix stopper, 4-heptanone. Good. This is the weird thing. You could also call this dipropyl ketone. And you can kind of see like propyl, propyl, ketone, which is why I think you can call this tert-butylaldehyde, because you're just describing a common branch. Why do it though? I don't know, right? It's like calling acetone dimethyl ketone. Sure, or you can call it propanone, 2-propanone. All right, and how many enols? Well, once again, we actually have this EZ isomerism. So there's technically 2 that could form that are EZ isomers. But the most stable is going to be the one that forms. So that would be the trans isomer. Oh, actually, that's the cis isomer. Sorry, that always gets me. That is the cis isomer because oxygen is a higher priority group than carbon, and carbon is a higher priority group than hydrogen. I don't know if I can actually rationalize that this one would be the preferred isomer, because it seems quite clear that this isomer has more steric strain in this configuration by having this ethyl and this propyl chain butting up against each other. But technically, this is the trans isomer, and this is the cis isomer. Well, lucky for you, I'm not going to ask you to predict which stereoisomer forms more readily. Mumtaz. Okay, well, it looks like I only took the alpha hydrogen from the left. Shouldn't I also take the alpha hydrogen from the right? Yeah, it's a symmetric ketone here, so either way I do it, it's actually the same enol. All right, let's actually jump ahead to our very last one. Do you guys remember the name of this diester? This is one I want you guys to be familiar with. It starts with an M. Yes. Methylmalonic ester or methylmalonate. This is our malonic ester, and we're going to use the malonic ester in some syntheses in this unit. How many tautomers? Yeah, just one. Again, it's symmetric, so either way we look, it's going to be the same. It'll be the same enol. Okay, interesting. When we take the enol of an ester, we get a geminal etherol, or like a vanillic hemiacetal. Remember the hemiacetal was a geminal etherol, and once again I have an etherol connected at the same carbon, but this time it's an sp2 carbon instead of an sp3. So definitely different chemistry, but that enol is distinct from the enols of our aldehydes and ketones. That enol also has an OR group attached to it. All right, then on to the last one up above. Do you guys remember the name of this compound? Yep, ethyl acetoacetate. You could also call it ethyl 3-oxobutanoate, but acetoacetate is how you'll hear it referred to. How many enols did you guys find for this? How many tautomer forms? 2? You want to describe one of them? Okay, from the methyl to the ketone, form an enol. What other enols did you guys determine? With which carbonyl? Okay, so we've got 2 more. From the middle to the ketone, and from the middle to the ester. Any others? I didn't think about this, but students in the fall actually pointed out that you could combine our bottom and top enols, and you could technically get this double enol. Enols in general are hard to form by equilibrium. They are less stable than their carbonyl form. So I think getting that double enol would be especially hard. And that's not always true. Actually, there are some dicarbonyls that prefer an enol in them because it allows for some stronger hydrogen bonding between the carbonyl and the enol OH. I just don't have good examples of them. So now you know, but you can't see it, haha. Okay, good exercise on determining enols. Looking for that tautomerization process, recognizing that these are chemically interchangeable. Okay, let's take a step back and look back at that part about ranking by acidity. I'll be honest, I kind of forgot how I was planning on doing this, but I think we can go through and rank from most acidic to least acidic hydrogen. Who would like to take a gamble at the most acidic hydrogen out of all of the hydrogens present here? Which one? It's got 2 alpha hydrogens, and then it's actually got these 2 sets of hydrogens as well on the ethyl. Furthest to the left is the most acidic. what distinguished that one for you from this methyl on the ketone? How were you able to rationalize that this would be more acidic than this?
Because there's more resonance on ethyl acetoacetate.
So I see resonance with that carbonyl and resonance with that carbonyl. But if I deprotonate here, this is an sp3 hybridized atom, so it blocks any further resonance.
Then I guess the middle one would be more acidic.
There you go. The middle position has twice as much resonance as the methyl. Good. So here is our lowest pKa. Let's call that acidity number 1. How did you rationalize that would be more acidic than the central alpha position on the malonic ester? More electron density. The esters are pushing electron density towards the alpha carbon, making it harder for it to be an acid. But because of that increased resonance, it is the second most acidic of our alpha hydrogens. Let's talk about what would be the least acidic. Let's go to the opposite end of the spectrum. This one might take us a little bit more rationalizing to get to. Can I hear your thoughts, Andy? Tertiary carbon of the ketone?
Yeah, just because it's a ketone instead of the aldehyde.
Okay, so you're saying in general just the ketone. Which side of the ketone do you think would be less acidic? Yeah? Less substituted? Because remember, acidity increases with substitution here. So we're just going to pick one acidic spot for each compound. So this compound number 5, that would be our least acidic spot. Maybe that's not the best way to do it. We can come back in and modify this. Oh, I screwed up, sorry. You see how I screwed up? I said the least substituted is less acidic, and then I labeled. Okay, well actually, maybe I didn't screw up. We can still label that tertiary as 5, and we can label the methyl as 6. Because the methyl would be less substituted than the tertiary carbon. I know I said I was just going to map one spot on every molecule, but now I won't. That one got 2 spots marked. Okay, can we fill in the gaps then? What's the third most acidic? Comes down to the aldehydes, right? It looks like isopropyl. Mm-hmm. Good. Tertiary over primary. More acidic, less acidic. Good. Now there are other hydrogens here that we aren't considering. Well, first of all, I didn't consider the methyl carbon here. I think you guys would agree those are very similar chemical environments, similar substitution, functional group, resonance. So those have similar acidities. We also are not considering here CH bonds that are not involved in any sort of resonance. So like the methyl group next to the oxygens on the ester linkages, or the ethyl groups on the ester linkages. Terrible, terrible acids. They have no resonance to stabilize them. We're also not considering the aldehyde hydrogens. These also have pKa's in the 40s. Maybe higher, sorry, 50s. Actually, it's quite hard to find pKa values for aldehydes. I've looked because I've had students come to me and say, I've got reason to believe that the aldehyde should be more acidic because of its placement with the carbonyl. And there's reasons to say no. It's not in a p orbital after it gets deprotonated, so it's not in resonance with the oxygen. But it's really hard to find people reporting the pKa of aldehyde hydrogens because they're just not that acidic. People don't care about their pKa because it doesn't happen that often. So I just want to say it one more time, reiterate. These aldehyde hydrogens are not being considered in the realm of acidity here for essentially the same reason that all of these other hydrogens are not being considered in the realm of acidity. They're just normal CH bonds. They're terrible acids. Cool. All right. Well, I want to talk to you guys about something more on this topic of acid-base chemistry before we get onto the back side of this and do alpha carbon substitutions. I want to talk about kinetic and thermodynamic bases. Oh, you didn't get it? It'll be on YouTube at the end of the day. Probably. Maybe. All right. So on the topic of kinetic and thermodynamic. There's actually two ways of looking at this. We can describe the base as being kinetic or thermodynamic, or we can describe the enolate that results, and therefore like the tautomer that results, as being the kinetic or the thermodynamic. What do you guys remember about these terms, kinetic and thermodynamic? Good. Yeah, and actually not just allylic, but usually in the presence of like a diene that reacts, let's say, with HBr at negative 80 C. It forms an allylic intermediate, and we get a 1,2 addition as opposed to running this at higher temperatures and getting a 1,4 addition. Temperature plays a role here, and the role was that the allylic carbocation can either go through a higher energy activation barrier and get to a lower energy product, or it can go through a lower energy activation barrier but get to a higher energy product. And that is exactly the same general map that we're going to show here. So this is energy, and this is a two-way reaction coordinate. We're going to show two different things that could happen from this starting point. One thing that will happen takes a lot of energy but yields a very low energy product. The other thing that can happen does not take as much energy, but does not yield as stable a product. Don't read into the colors too much. I change the colors every semester. You're just lucky I'm giving different colors. Okay, but what about the term kinetic and thermodynamic? How do you know which one applies to which? What do you think of? Good. Kinetic happens faster. Thermodynamic is more stable. When you think of kinetic, what do you think of? Think of like kinetic energy, motion. It turns out you need kinetic energy no matter what. So it sometimes can be hard for me to say kinetic means faster, because to me kinetic just means move. So I remember this by thermodynamic. That is the product that has the most dynamic formation. It requires the highest energy and it produces the most stable product. The highest high and the lowest low, the most dynamic. That is what we're showing here in blue. Thermodynamic. If you can remember one, then the other one is easy to remember. It's the other. But I do like what you've said, Milena, which is kinetic is the one that happens fastest. If I start putting energy into my system, imagine I've got a ball rolling up both of these hills, and I'm adding more and more energy as it goes, it's going to roll over the smallest hill first. That is the reaction that happens quickest. It requires the least amount of energy, so as soon as that energy threshold is met, that reaction happens. Meanwhile, I'm still halfway to my other energy barrier. So let's take a ketone, because this actually doesn't apply to aldehydes or esters, which only have one position. This applies best with ketones. 3-methylbutanone. And let's fill in what the enolates look like. So we're going to introduce a base either way, but let's figure out what the enolate looks like. Well, the most stable enolate is the one that is more substituted as an alkene. So my tri-substituted enolate, that is my thermodynamic enolate. That's the more preferred tautomer, conjugate base. The less substituted side gives me my kinetic enolate. Why can we suspect that the more stable enolate, the more stable conjugate base, takes more energy to form? It has to make sense. There has to be a reason why. Any suggestions? If a base comes in and takes this hydrogen, why does that require more energy than taking this hydrogen? Mm-hmm. What about it?
It's like the hydrogen attached to the carbon as well as substitution.
Yep.
Therefore, that means it's more acidic.
Well, it is more acidic because it's more substituted, because the base is more stable. But why does it require more energy? If it's more acidic, why does it require more energy to pull off?
Is the base like a strong base, like an SN2 mechanism or something? Or not in E2 mechanism?
It's not technically E2. E2 requires like a leaving group. I guess you could think of it as E2 because you break the pi bond. So yeah, it's one step. I think that's what you're saying. It is one step. The base comes in and pulls off the hydrogen. Elliot, you said a word that nails it on the head.
Sterics, because if it's really cold, they're not bouncing very fast, so it's going to probably get the outside one first, rather than like really smashing together.
Yep. This tertiary position has more groups around it, like James said, which means it has more steric strain. So for a molecule to get in close, Elliott's description of needing more energy to ram in, break past all of that steric strain, and rip off that hydrogen is needed. At the less substituted position, I need less energy to actually get my base to ram in. There's less steric strain pushing it away. So what would we use? Well, a lot of times our thermodynamic bases are small things like sodium hydroxide, sodium methoxide, sodium ethoxide. I want to point out that I'm writing methoxide and ethoxide a couple of different ways. I can write NaOCH3 or NaOMe, and I can abbreviate ethoxide as OET. We might do that more in this chapter, in this unit, than before, because we'll be using those bases more, and it's just kind of common to abbreviate them. So these are thermodynamic bases. They themselves have very little steric strain. So for them, this energy gap is basically negligible. This energy gap between thermodynamic and kinetic isn't impacted by their size. So they're able to overcome this energy gap. But if I create a base or bring a base that has a lot of its own steric strain as well, this energy gap exaggerates even more. So our thermodynamic base of our kinetic base of old, our big bulky base, tert butoxide. We're going to introduce a new one. We're going to introduce LDA. Did you get a picture of this? Okay. What do you guys think you might confuse LDA for with a previously learned reagent? LAH, LiAlH4, lithium aluminum hydride. I can see that. It shares some features. LDA is lithium diisopropylamide. Big and bulky. And actually, more than that, it's bulkier than tert butoxide. It's got more carbons. Oops. Those carbons are branched out more because they are on two different groups. So it is bulkier, but it also has a very other stark difference from tert butoxide. In terms of being a base, how does LDA compare to tert butoxide? Tert butoxide also has a negative. They both have a negative charge. Oh, no, that's a good point. They're similar in that they both have a 1 minus charge. How are they different? How can you claim so confidently that LDA is a stronger base? We can blame it on electronegativity. So they have the same charge, but they are different atoms holding that charge. Nitrogen is far more willing to share. Oxygen is more willing to keep its electrons. So LDA is bigger and stronger. And that's one of the reasons why we're going to use LDA. All right. So now we've got regio control. We've got our thermodynamic bases and we've got our kinetic bases. Before we look at some of our reactions, I just want to introduce why we might use some of these different reagents at different times. I'm just trying to think if this may not be the right time. So this unit is 2 chapters or 2 sections they overlap quite a bit. They're quite similar. We're going to use the LDA more though in the second section. So I'm debating whether it's worth bringing this up now or coming back to it. I think it might be worth coming back to it. So let's just keep a pin in that. LDA, bigger, stronger. But we're going to come back and take advantage of that later. We're going to talk about how well it can turn something into an enolate. For now, let's focus on the first set of reactions that we're learning in this unit. We're looking at the alpha carbon substitution reactions. We will use LDA in our condensation reactions in the second section. All right, take a look at that first reaction diagram that I've given you. What do you notice? I heard something. Come on, you got to notice something.
We have reactions with both the more and less acidic.
Okay. Reactions at the more acidic and less acidic, the more substituted and the less substituted. What else? Okay, they're all with bromine. I like bromine more than chlorine, I think, for some reason. And there's no, the Grignard could be any halogen. The Grignard just uses magnesium. Yeah, although when you did it in lab, you had it with a bromine. But there's no need, doesn't need to be. I think I just like bromine the most. Okay, so there's reactions at both sides of the ketone, both alpha carbons. 3 of them are all giving the exact same product. So I'm going to show you 3 different ways to do the exact same thing. What else? One's a dihalide. Good. All right, so the first way that we can substitute an alpha carbon, and by substitute, what I mean is substitute a hydrogen there, just like how we did EAS, and we substituted a hydrogen. We can take advantage of the stability that the alpha carbon has in resonance. with a radical. So we can do Br2 and light. Remember that this is a radical reaction, which means the intermediate that forms is the most stable radical intermediate. How can we rank radical strength? Radical stability, I mean. Radicals trend with carbocations. Carbocations are more stable on more substituted positions. Radicals are more stable on more substituted positions.
Electronegativity doesn't matter.
Well, there's only one hydrogen that can be abstracted here. It's carbon to hydrogen. Is that what you meant?
Oh, well, because I'm saying, like, it ends up on the oxygen.
Oh, it doesn't end up there. Neither of those exist.
Well, I'm saying, like, is it more likely to end up on the oxygen because the oxygen is more electronegative?
Okay, great question. Does the resonance hybrid, the actual molecule that is some mixture of these resonance forms, does it actually have the radical on the oxygen more than on the carbon? Yes, the orbital on oxygen is a little bit larger than it is on carbon, but it's more stable on the oxygen and it's more reactive from the carbon. So the reason that this radical even forms, this radical forms very quickly, very well, is because it's in resonance with an oxygen. But the resonance form that reacts is the one where carbon holds the radical. Because oxygen would rather hold it by itself, carbon would rather share it. Carbon's less electronegative, more willing to share that electron. Good question. By the way, in my OChem 1, I got to bring up MO theory again. I just love it so much, so I want to share it with you guys too. This is the resonance form that's created. I've got a pair of pi electrons across both carbons and the oxygen. And then I've got a radical electron in a molecular orbital that skips the carbonyl carbon. So the molecular orbital is saying this electron is not on carbon or oxygen. It's on both of them at the same time. I just can't draw that at once. I have to draw it as two separate forms, but the orbital that the electron is in sits only on the carbon and the oxygen. And then, of course, the next highest energy, all of the p orbitals are out of phase with each other, but it's unoccupied. This is really the interesting one. Okay, the next way that I can substitute at this more substituted position is if I have elemental halogen in the presence of H3O+. Yeah, I agree. That's weird. Is that what I interpreted from your face correctly? What will H3O+ do with this ketone? It will turn it into its most stable enol. Remember, we looked at the mechanism for tautomerization in basic and acidic conditions, and we know that the acid tautomerizes the carbonyl, and that can actually make a base out of the alpha position. Now the alpha position has electrons that can attack bromine. If you guys are interested in these mechanisms, we can go through all of them. I just won't test you on them. The other way that I can substitute at this more substituted position is to have my elemental halogen and hydroxide. Because what does hydroxide do? it makes my more substituted enolate. And once again, that means I've got something basic from an alpha position and more substituted. All right, well then the question stands, how do I halogenate the less substituted position? If radicals go to the most stable, acidic conditions go to the most stable, and basic conditions go to the most stable, what can I do? Yes, so I think you're saying the alkene just needs to be on the other side, right? So how do I make the alkene there? What reagent could I introduce? Oh, okay. Any recommendations?
Oh! Well, I don't know. What, LDA?
We could do LDA. We'll actually come back to work with LDA in the next section. LDA wouldn't, that's why I wanted to not introduce what LDA will do yet, because it's just not, I don't think it would be commonly used here. We could use LDA, or we could use terp-butoxide. And actually, once again, we'll use our elemental base. So I'll put this in here, terp-butoxide or LDA, which means we're actually running in basic conditions. Okay, so we've already taken advantage of our thermodynamic and our kinetic bases. One thing that I'm not saying here, and I know this will throw some of you off, is that the bromine is assumed to be in excess. We have an excess amount of bromine. So it's not Br2 adding once at the alpha position. It's actually two equivalences of Br2. And if we want to specify that, we just add next to Br2 excess. I actually just had a chat today with Chris Peak. We have bromine upstairs in our lab. It's not something you like to hang on to. It oxidizes stuff like crazy. We used to keep it underneath one of our fume hoods, and that fume hood is just totally rusted out. It's nasty. So since then, we've been keeping it in the fume hood in the stockroom. But it evaporates. It's hard to store. It's scary to work with because you spill it on your hands and it will oxidize you. And he was dealing with it with OCHEM 1 labs. Do you guys remember in OCHEM 1, when you do the dehydration of the alcohol and you form an alkene, and then you drop some bromine in and mix it to see if the bromine disappears, proof that it reacted with an alkene, proof that you have an alkene. He was like, can we just throw this? We don't need this. We really don't. Bromine is just not worth having. So, fun stuff. Just because you can use bromine doesn't necessarily mean that you want to use bromine. Anyways, after you wrote bromine 4 times in excess, now you know. All right, I want you to think about the fact that this kinetic base actually gave us 2 equivalences. Let's remove ourselves from a situation where we have kinetic and thermodynamic. Let's get to a spot where we just have one alpha position, and let's make that alpha position just a methyl group. So to your top right, we're going to work with acetophenone. What did did I do with it? It's just going to two things. Good. And did I show you what those two things are? I don't know why I can't remember this for the life of me. Did I do this right? Was the mono substituted on the bottom right? Dang it. Just going to start over because I didn't give myself enough room anyways. I've got three alpha hydrogens. Only one of them gets substituted. The conditions that do this for me, Br2 and acid. Acidic conditions depend on that alpha hydrogen being, depend on this oxygen being basic. Having the halogen present really changes the whole dynamic of this system, and it makes it harder and harder to tautomerize. In acidic conditions, this is less reactive than its precursor was. By halogenating, I have inhibited the ability for tautomerization. So acidic conditions monohalogenates, and then it stops. In basic conditions, the monohalogenation doesn't stop, which is why we saw here in basic conditions, I can substitute both of the alpha hydrogens. But now we're finding in basic conditions, I can substitute all three of the alpha halogens, and I can cleave the carbon off of the carbonyl carbon entirely. So this is typically done with Br2 in excess and NaOH in excess. And this is called the haloform reaction. This compound up here is called bromoform. A relative to the knockout gas from the entertainment industry, Hollywood, movies. Chloroform, which, by the way, doesn't work like they show in the movies, so I've heard. Yep. Where'd you hear that? I don't know my source.
My coworker, he's older, but he was like, "What chloroform doesn't work like that?" And I was like, "Why would you know this? I don't know, who are you?" But yeah, I think he knows something about it, but when it was used for anesthesia,
Right.
But yeah.
Turns out you need a pretty large amount of chloroform to be able to knock somebody out, and by the time you've got that quantity, you have enough that you could kill them. So it's really easy to just kill somebody with chloroform and not just knock them out. So in the movies when they pass out, it doesn't really work that way. But as it turns out, chloroform is just the chlorine derivative of the haloform. And the haloform reaction occurs in basic conditions with a methyl carbonyl. It requires a methyl group because each of those hydrogens needs to become a halogen, needs to be substituted. Then the base actually plays a big role in doing part of the cleavage. So this is definitely a mechanism that I want to show you guys because I think it's really fun and it shows that repetitive behavior of the chloroform reaction. And I think we can pair that with a reaction like this. Well, maybe we do the same version. So we can show how acidic conditions compares to basic conditions and why it's not as reactive. But first, why don't we do a break? Let's take 5 or 6 minutes and come back here at 10 after. Any halogen.
And then it's the H3O plus any acid. Or does it have to be H3O plus?
No, I think any acid will work there because H3O plus is really hard to store in a lab room. You don't. First of all, it's got to be balanced by some counter ion.
Okay.
What is that counter ion? Sometimes it's chloride, which means the acid that you're storing is actually HCl. You're just storing hydrochloric acid, which has dissociated into hydronium and chloride. The counter ion could be sulfate. So you'd have 2 hydroniums to 1 sulfate, which means the acid you're actually storing is sulfuric acid. So when we say H3O plus, what we actually mean is use an aqueous acid.
Okay.
HCl, H2SO4, they really all do the same thing. Same, but different. Good question. I was working with a Gen Chem 1 student today in office hours, working on oxidation states. And I said, why don't you draw the Lewis structure for sulfuric acid, and we'll determine the oxidation state of sulfur. And their instinct, so they knew the sulfuric acid was H2SO4, and their instinct was put the least electronegative in the middle, bond everything else to it. And they said, I don't know why I'm allowed, oh, right, sulfur is row 3 or bigger, so sulfur is allowed to have 6 bonds. You know what? I get it. Yeah. Nowhere in that formula does it suggest to you that the oxygen is bonded to the hydrogens. And I don't think it ever comes up in the learning software, and I don't think it ever comes up on the exams, but that's sulfuric acid. How would you know that from the chemical formula? There's no reason to suspect it. And that made me realize that I could very well be raising children all the way from Gen Chem 1. Children was not the right word. Raising students all the way from Gen Chem 1 to OChem 2, and they potentially have never seen the structure of sulfuric acid in my own classes. Oops. I think I need to do more structural drawings more often. I don't know. It's crazy. I remember sulfuric acid from my Gen Chem 1 class, so what am I doing wrong that my professor did for me, but I'm not doing for you guys? Crazy. Well, I mean, what test? If you took chemistry here, you would have never had a test that said what is the correct structure of sulfuric acid.
In lab, we had to do that paper thing and we draw it out. I might have got that wrong.
In OChem 1,
Yeah.
you had to do a paper thing and draw it out.
Do the Lewis structures for a bunch of stuff.
In lab?
I think it was a lab thing. Pretty sure.
In Gen Chem 1 lab.
Yeah.
We don't do that structure. Yeah.
Well then, yay, I didn't get it wrong.
Actually, I think the best way for me to approach this is, and I'm teaching Gen Chem 1 again this fall in person, and I'm so looking forward to it. It is so hard to teach online. I mean, I feel like I'm not doing it. I'm not teaching. I'm just like checking their grades and trying to send them messages and meet with them, but not half of them don't meet with me. In the fall, what I'm going to do is really lean into the compounds they need to know. The polyatomic ions and the acids and maybe a few organic compounds. Like they need to know acetic acid, but maybe I'll like make sure they know how to draw methane, make sure they know how to draw glycine. Is glycine the like 2-carbon amino acid? The simplest amino acid there can be. Just like basic stuff. And early on in the semester, I know they already are being told memorize these polyatomic ions, but I think I'm going to really nail it into them to know them. And then by the time we get to the Lewis structures, why draw a bunch of random stuff? Draw all of the ions that I told you to memorize. So all of the acids, all of the ions, all of those really common basic organic molecules, know how to draw them. If I'm asking you to know the chemical formula of an acid, I would really hope that you can see the Lewis structure of the acid in your brain. Because I can. And I think that's the expectation most professors have without necessarily putting it into words, you know? But a lot of times we just draw random stuff, meaningless stuff. I was doing a research project with the geosciences, and we made aqua regia, which is a super caustic acid solution. You mix 3 parts of hydrochloric acid with 1 part of nitric acid. And that combination of HCl and HNO3 mixes together to create a compound called nitrosyl chloride. And that is the chemical that does what neither of the acids on their own could do. That chemical oxidizes gold and turns gold into ions. Not a lot of stuff oxidizes gold or silver or platinum or palladium, but aqua regia will. Aqua regia oxidizes so much. That's what I gave to the students that were on the geoscience project. I said, here's the chemical that's responsible for helping us dissolve your samples. Do you know what it looks like? If you don't want to be on the camera, you could draw it in the corner. Yeah, you're off screen all the way to here. Do you know the first rule of Lewis dot structures? Yeah. Yeah, it depends on who you ask is the first rule. When I teach it, the first rule is count your valence electrons so that you know exactly how many electrons to use. And then rule number 2 is place the least electronegative in the middle. So that goes N with oxygen on one side and chlorine on the other. It doesn't matter where. Why? Why should N go in the middle? I think I said it. Least electronegative. Most willing to share with everything else. Then what? Single bond everything. You should single bond all of the atoms, because there might be double bonds, I don't know. And then recount your valence electrons. So I had 5, 6 is 11, 7 makes 18. I've got 18 valence electrons. I've used up 4, so I've got 14 left. What should I do with those remaining 14? And I like to put lone pairs on the outside atoms first, because if there's going to be lone pairs anywhere, it's going to be on the outside atoms. So 2, 4, 6, 8, 10, 12. I ran out of space on the outside atoms, so I'm going to put another lone pair on the center atom. 14. Next rule. Obey octets. So move lone pairs in to make double bonds and triple bonds. And if you're already familiar with common bonding patterns, then you know chlorine is happy with just that one bond. But oxygen is not. Oxygen likes two bonds. And nitrogen is short a pair of electrons, so oxygen can make that happen. Now everything is satisfied. Formal charges are 0. When I teach Gen Chem, I don't think I did this for you two, but in the fall, I started by teaching them common bonding patterns, kind of like what I did with you guys on the first day. These are the charges and these are the ways that it can bond. Because that is the pattern I want people to recognize. Know that halogens bond once. Know that oxygen bonds twice. Know that nitrogen bonds 3 times. Get familiar with what charge is going to be on it. I introduce formal charges before I introduce Lewis structures, because most of the time your Lewis structure can be predicted by the formal charge. What's the first rule of a good resonance contributor? Minimum formal charges, right? That's a fundamental to drawing a structure, is minimizing formal charge. The way that the textbook we use in Gen Chem 1 teaches formal charge after Lewis structures. I don't get it. Okay, there it is. And then, of course, if we wanted to obey its molecular geometry, it's got a bent shape. Very cool.
So why is it so good at oxidizing?
I don't know. So in order to oxidize something, this needs to get reduced. So this is going to pull electrons out of something else. The chlorine would be happy to form chloride and take electrons away from things. But I can also, I don't know, really. Actually, I think a better way of saying it is that the chlorine can bond onto other things and give the electrons back to this group and take electrons from that thing. I think the oxygen can also take electrons from that thing. I don't know why it's so good. I'm not used to seeing mechanisms for stuff like that, to be honest. It's possible that this produces chlorine gas. That would reduce. No, that would oxidize the chlorine. Yeah, good question. For some reason it is. Good at oxidizing. Okay, oh, thanks for that, letting me rant like that. Felt good. You guys want to do some mechanisms? Mm-hmm. Are you interested? I'm not going to test on these. Yeah?
Let me understand how the reactions work, though.
All right. Should we start with a mechanism for the radical reaction? Are you interested in that? Okay. Are you all right if we simplify the structure a little bit, just so we don't have to draw that whole ring? All right, well, in the presence of light, elemental bromine can initiate radicals. That means starting from no radicals, bromine will homolytically cleave its bond and form 2 bromine radicals. Then bromine will abstract a hydrogen Remember that I'm using fishhook arrows here. That means I'm describing how many electrons moving? Just 1. And when I want to form a bond between 2 fishhooks, they just meet up in the same place. So this is showing bromine radical and hydrogen radical forming a bond. And then carbon radical and carbon radical forming a bond. And I am showing you, like you guys pointed out earlier, I'm showing you the most stable resonance form, but not necessarily the reactive form. You wouldn't have to do this. You could show the carbon radical where it is. Then in the final step, the termination step, that alpha carbon and the bromine radical terminate. Alpha halogenation by radical substitution. Me
But-
either. Sorry.
But the bromine substitutes onto the more substituted carbon, right?
That's right.
Okay, because that's why, because technically there's 2 alpha carbons.
That's right.
But it goes to
It goes to the more substituted because that radical forms on the more substituted carbon. Because a more substituted radical is more stable. All right, now let's show the alpha halogenation in acidic conditions. Yeah? Well, you know what? I guess we could have done this with the aromatic ring example. So for acidic and basic conditions, let's show the halo form, which is just basic conditions on repeat. What's my acid in acidic conditions? H3O plus. What's my base? The oxygen is the only thing that can be my base here. So oxygen gets protonated. The conjugate base is water. And water will deprotonate the alpha carbon. What have we just completed here? Tautomerization. The acid has tautomerized my carbonyl into an enol. And as we learned in OChem 1, alkenes can be nucleophiles. Alkenes can attack. Actually, what we saw in OChem 1 was an alkene attack Br2 and make a bromonium ring. But this is not just an alkene, is it? This is an enol. So it has resonance from the alcohol. The alcohol is in resonance with the alkene, so it's not going to behave just like an alkene would. Instead, the alcohol helps push electron density from the alpha carbon to the halogen. It behaves a little bit more like our EAS mechanism, where the aromatic ring attacked bromine, except we don't need a catalyst. So my carbon has now bonded to bromine, and I'm left with bromide. I also have my acid catalyst here, my H3O+. And I'm not in a great spot for showing the next step of my mechanism, so I'm just going to shift it down. Because the next step of my sorry. Next step of my mechanism is deprotonation. And here I can say bromide takes that hydrogen since my catalyst has already served its role. And that's where the mechanism stops. It now is terminated because in order to protonate and then deprotonate again, the H2O is just not a strong enough base to do a subsequent deprotonation anymore. Acidic conditions just is not reactive to this monohalogenated product. I need a stronger base. And when I get a stronger base, it's actually the addition of the halogen that is a feedback loop and makes it more and more reactive every time in basic conditions. All right, so this is the haloform reaction. That's the mechanism we're going to see here. What I'm going to do is write out all of the equivalences of base and halogen that I will use. And I'm going to keep those equivalences throughout each step. And as an equivalence becomes useless, I'm just going to put it in parentheses and stop drawing it and refer to it as a byproduct. In acidic conditions, my first thing to do is protonate. In basic conditions, my first thing to do, deprotonate. Where's my acid? The only hydrogen. The alpha hydrogen, surprisingly acidic. So hydroxide acts as my base and deprotonates to form my enolate. I form a molecule of water. That's going to go away. That's a byproduct now. I still have 3 equivalences of my base left. I've just formed a nucleophile. My enolate is nucleophilic from the alpha carbon. I just formed a byproduct of bromide. I guess if I were being specific, I'd show the counter ion. Maybe I'm using sodium hydroxide, so I now have a byproduct of sodium bromide left over. I'm in basic conditions still, and in fact, my alpha carbon has just become even more acidic. It has a halogen attached to it now, and that halogen has an inductive effect that says, take this hydrogen next. So the next alpha hydrogen becomes deprotonated, and once again, I just want to clarify, I'm showing the formation of the major resonance form rather than the reactive resonance form. But I could be showing either or both. I've just formed another nucleophile, so it's now the same thing. Carbonyl reforms. Alpha carbon attacks the electrophile, the halogen. I just realized I forgot my bromine. That means in this step I kick off a bromide byproduct. My third alpha hydrogen is the most acidic that any of them have been. It now has 2 halogens directly next to it, pulling away from the carbon, telling the carbon, if you take a negative charge, we will help stabilize it. So hydroxide comes in for the 3rd time, deprotonates the final alpha hydrogen. Produces a 3rd byproduct of water and sets up for the 3rd nucleophilic attack on bromine. I've not shown my last hydroxide here. So I'm going to rewrite this now as CBr3. And in this step, I produce my final byproduct of bromide. Whew. Now that carbonyl carbon is more electrophilic than it has ever been because adjacent to the carbonyl carbon is a strong inductive effect towards the bromines. Seriously, they're taking electrons towards them, leaving a big partial positive on the carbonyl. So the excess amount of hydroxide gives me acyl addition. Actually, I'm going to just swap these because I know sometimes the order in which they're drawn can help make sense. Now, typically, we say that a good leaving group would be something like chloride, or even a carboxylate would be a good leaving group. So like when the acid anhydride gets attacked, a carboxylate can get kicked off. But we say that like a carbon group is never a good leaving group because it has to leave with the electrons. It would have to leave as a negatively charged carbon. No carbon can do that better than a haloform carbon. If that carbon leaves with the electrons and takes a negative charge, it's got 3 halogens that will help stabilize that negative charge. So this tetrahedral intermediate collapses and kicks off CBr3. But I have just formed a carbon base in the presence of a new carboxylic acid. So that carbon deprotonates the carboxylic acid. And I'm left with a carboxylate that used to be a ketone. And I'm left with my halo form, in this case, bromoform. And a word of caution, you can do this yourself accidentally. People have done this to themselves accidentally and died. Chemistry is a scary place. God, what other classes tell you so much about death? Why do I tell you so much about death? If you accidentally take like acetone, which is a methyl carbonyl, and mix it with bleach, which is a Cl2 producer, a chlorine producer, and lye, which is a source of sodium hydroxide. People have mixed that all together. I don't know whether it's on purpose or not, in a toilet bowl, and they've created the haloform reaction in their toilet bowl. Acetone, Clorox, and lye. All things that you can buy without an ID. Okay, truth be told, these people maybe were trying to do mischievous things, right? And they thought, I can create dangerous chemicals at home in my toilet bowl. You know, if you're trying to make a big batch, where else are you going to put it? You want a lot of water to dissolve it. A toilet bowl is really just a round bottom flask at the end of the day. Very dangerous, though, because if you mix all those things at home, you die. So be careful about the chemistry you do at home. I myself, I keep no chemicals in my home. I'm never home, never even myself, because I'm chemicals. No, it was a joke. No food, no water. In fact, my house doesn't exist because that would be chemicals. All right, cool. Let's talk about a few more. Reactions down here on the bottom right before the put it to work part. These are also alpha substitution reactions, but you'll notice that now we're using our acetoacetic ester, acetoacetate ester, And that's because what we want to do next really does require a good nucleophile. So we want the most acidic proton so that we can make the good nucleophile. In general, this is just commonly done with these beta carbonyl carbonyls. I do want to ask one question first. Do you think that it would matter if I had swapped out acetoacetate with malonic ester? Would it have made a difference? No. The acetoacetate could easily be swapped out here with a malonic ester because they share the same principle of being this beta carbonyl carbonyl. And that's really what we're going for. All right, why don't we fill in the one thing we know, which is up. What is that reaction going from our beta carbonyl carbonyls up? What's happening? You guys did well on the unit 3.
We're going from the ester to the carboxylic acid.
Ester to carboxylic acid. A little bit more. We need H2O and H+, in which case we can write H3O+. Hydrolysis of the ester. We've already learned that. What about this? I actually forgot to add this one in here. What if I took either of these and I mixed in NaOH? What happens? This one gives us saponification, where let's say I'm working again with my ethyl acetoacetate. Hydroxide attacks, just like we saw here, and it kicks off the ester linkage as a leaving group. And that ester linkage, just like we saw there, then acts as a conjugate base. All right, can't use hydroxide with our esters because hydroxide will saponify our esters, and that's not what we want. We want to do some substitution chemistry. On one side, we're showing a dye substitution. And it's not substitution like we had before. It's not halogenation. Now we're doing what? Alkylation. We're adding alkyl groups to our alpha carbons. On one side, I'm doing dialkylation. On the other side, just monoalkylation. So, can't use acid. That will hydrolyze the ester. Can't use hydroxide. That will saponify the ester. How am I going to turn these carbons into nucleophiles to do alkylation? I just use a different base. Did you say imagination?
It's imagination.
I'll use a base that works like hydroxide, but a base that won't hydrolyze or saponify. What base works like hydroxide but doesn't do saponification? A base that matches the ester. So if I'm using a methyl ester, then the base that I want to use is a base that matches that ester linkage, a methoxide group. If I'm using an ethyl ester, then I want to use an ethoxide base. I need a base that could absolutely attack my carbonyl carbon, but if it kicks off a leaving group, that leaving group is whatever attacked. Does that seem fair?
I don't get why we care if the side chain on our base matches.
If I use hydroxide, I don't get an ester anymore.
Right, but why do we care if if it's an ethyl versus a methyl?
If I have a methyl ester, but I add an ethoxide base, I can transesterify. And if I do transesterification, if my base attacks and kicks off methoxide, leaving it now as an ethyl ester instead of a methyl ester, now I've got different properties. It might be hard for me to actually, and not that those properties are like always life or death, but it could just be a matter of making it hard to purify. So I want to just make sure that I started with an ethyl ester, I end with an ethyl ester. All right, so since we're working with our ethyl ester, that's what we'll use. We'll use an ethoxide base. But I want you guys to recognize that if I swapped this for my malonic ester, or if I were using methyl esters, I would just swap out for a methyl base. All right, so to the left, what I want to do is create a nucleophile and then have it be a nucleophile on some electrophile. So first, I'll introduce something like ethoxide, which will react with my carbonyl carbon and make a nucleophile. And then I'll introduce an electrophile with a good leaving group, methyl iodide, methyl bromide, methyl chloride. And if I want to do this twice, well, the first time that I alkylate, my alpha carbon gets more acidic. Same amount of resonance, but now it's a higher substitution. So first, deprotonate, then alkylate, then deprotonate again, then add in whatever second alkyl group you wanted. And I know I'm running out of time, so I think I'll have to send you home over the weekend to do the practice problems on the bottom, and that's where we can pick up next week. The nice thing is we're like really well on schedule, so that's good. Yes, yeah, I mean, it's not like you can only add methyl and ethyl, but it works best on primary carbons, methyl and primary carbons. So should we look at the mechanism for one of these? I mean, to be fair, this mechanism requires that we show the mechanism of 2 steps. So I'll show the mechanism of deprotonation, and then I'll show the mechanism of nucleophilic substitution. And let's switch it up a little bit. Let's show what it looks like on the malonic ester.
CH3O and then MEO are the same thing, right?
That's right. Yep. 2 different ways of just abbreviating methyl. Abbreviating. It's not much of an abbreviation. For example, a new carbon chain. So step 1, deprotonation. And I have a personal preference. I like to show the major resonance form but I actually know some students here have said drawing the minor resonance form, drawing it where carbon holds the negative charge, helps them understand the nucleophilic attack better. That's step one. Step one is done. And equilibrium slightly favors that step because the alpha carbon is more acidic than the alcohol. So the reverse reaction isn't as favorable by strength of acidity. After this is done, I introduce my electrophile, and my nucleophile just does simple SN2. I think the hardest part about this reaction is mapping the carbons. So remember, I like to count through my nucleophilic attacks. Carbon 2 attacks carbon 3, and then I've got 3, 4, 5. So when I draw my final product, carbon 1, 2, 2 attacks 3, 3, 4, 5. And of course, I kicked off a chloride byproduct. Add more base, repeat. I can only do it twice, unfortunately, but I can alkylate 2 times. All right, so we showed that we can hydrolyze. I guess maybe I didn't show that we get an alcohol byproduct when we hydrolyze up there. And then I showed that you can take this beta keto acid. Would you have called it that? I want you to call it that. I want you to recognize that it's not just a carboxylic acid, but it's a carboxylic acid with a ketone or any other carbonyl on its beta position. And we can convert this into a carbonyl and carbon dioxide. And the reagent that we need to do this is warmth. No, but for real, we just heat it up. This is a reaction called decarboxylation. And I only know of decarboxylation in one context, and that is the context of taking certain organic molecules made in nature in plants and heating them to a point where they decarboxylate and change the chemical nature of those plants before they're ingested for their psychedelic effects. What's that? It was about as scientific as I could say that. So decarboxylation on its own looks a little bit meaningless, right? If I take this acetic ester, that's really a hard name to say, acetoacetic ester, and I decarboxylate it, I get carbon dioxide and acetone. Great, so now I know a source of acetone. Why would I want to do it? Well, if I have just added a new carbon chain, then I can hydrolyze my esters and decarboxylate them. Sorry, I wrote that as 1,2, but it really doesn't need to be 1,2. And I showed you that the beta keto carbonyl gives just a ketone, but what happens if I have a beta acid acid? Well, again, I'm just going to cleave off one of those carbon chains. Sorry, one of those carbonyls. The other carbonyl just gets left as is. This gets hydrolyzed, decarboxylated, CH2, 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 or 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I can create new carbon chains by alkylating my alpha position and then decarboxylating one of the carbonyls off. And I can be left with a ketone, if that's the carbonyl I have. I can be left with an aldehyde, if that's the carbonyl I have. Or I can be left with an acid, if I have an ester that gets hydrolyzed to an acid. Do you want to see the mechanism for that? After it's hydrolyzed, we've already seen the mechanism for hydrolysis. So let me take this structure after it's been hydrolyzed. I like how I asked, but I really didn't mean it. I was going to do it. I was going to do it anyways. After it's been hydrolyzed, and once the heat gets pumped into it, it takes this conformation, and it goes through this beautiful intramolecular decarboxylation. Damn, that was a bad marker for that. And then we just get the enol, and the enol tautomerizes back into the carbonyl. And I apologize for taking you over, just for my own vanity. Thank you guys for your time. Put to work some of those reactions on the bottom of that sheet, and we'll solve those at the start of class on Tuesday. And get started on your active. You've got everything you should need for your active. Have a good weekend.